Hello everyone, welcome to another video of Calculus 1. In this video, we are going to talk about one of the very important theorems in calculus, as called mean value theorem. Mean value theorem says that if assume f is a continuous on the closed interval AB and differentiable on open interval AB, then there exists at least one value C in AB such that f prime C equals f of B minus f of A divided by B minus A. Let's see what does this really mean graphically. Graphically, I draw a graph. Something like that, and then have 2 points A and B. This is the closed interval, and this is FA, and this is FB, and I can actually connect those 2 points like that. And now I can move. I can draw parallel lines parallel to this secant line, right? The secant line, I can draw lines parallel to this secant line. This dotted line is parallel to that, and at some point, one of these parallel lines would be is tangent to the curve of the function. So that point, that point is C, right? So if that point is C, right? If that point is C, what is this one? This one is the slope of the tangent line, which is actually f prime of C. And then this part of the equation is the slope of the secant line, right? So what does that mean is that slope of the secant line is equal to the slope of the tangent line for any at some point C, right? So that's what mean value theorem means. So you can draw a secant line through two known points that going through two known points, and you can find a, a tangent line with the same slope, a tangent to the curve with the same slope. That's what it says. That's called mean value theorem, and that C is in between A and B, right? And that C is in between A and B. Now, this theorem has many consequences. What if we find that for any distinct values of A and B, for any distinct A and B values, let's say A1 and AB1, which are any values in between uh, A and B. So these are A and B, any values uh, in close uh, interval A and B, and I find that FB1 minus FA1, right, for any two values, FB1 and FA1, I find that this is equal to 0. But from the mean value theorem, I see that FB1 minus FA1 is equal to FC, some FC1 value times B1 minus A1. And you obviously know that these are not equal to 0 because A1 and B1 are two distinct values. So this is not equal to 0. Now, what makes this difference 0 is being F prime C1, right? F prime C1 is equal to 0, right? So that means if you have for any values A1 and B1, FA1, A1 and B1 such that FB1 minus FA1 is 0, that means in between those two values, FC1 is equal to 0. That means Fx is constant on AB, right? So we say that if F prime x equals 0 for all x values A and B, Fx equal constant. Fx equal constant. It's a constant function. So that's the consequence of, we can prove that by using the mean value theorem. And that's about constant function. And also, uh, we know that there are increasing functions. So what is an increasing function? If you have a function like that or like this, right? Now let's look at what is the tangent, slope of the tangent line drawn to these curves. These are increasing functions, right? And the slope of the tangent line f prime of x is greater than 0 always. And here in this case as well, f prime of x is greater than 0, right? This is f of x, and that is x. So for increasing functions, f prime of x is greater than 0, right? For increasing functions, f prime of x greater than 0. So if you define increasing functions, that means for any function f of x, if you have f of x1 greater than f of x2 for all x1, x2 in a b, such that x1 is less than x2, that is an increasing function, right? That's an increasing function. And for an increasing function, if you find f prime of x for that interval, it's going to be greater than 0. Now for decreasing functions, so if you have decreasing functions, either this function or uh, or this function, right? So you can draw a tangents at any points, and here is the same. Here's the same tangent at any point. This tangent line, slope of the tangent line, that is the derivative at the respective locations, f prime of x less than 0. So for decreasing functions, f prime of x less than 0. For decreasing functions, f prime of x is less than 0. So how do I define f decreasing function? F of x, f of x1 is uh, f of x1 is uh, so here I made a mistake. This should be uh, less than x2. So this is f of x1 is greater than f of x2 for all x1, x2 in AB such that x1 less than x2. So here increasing function f of x1 is smaller than f of x2. That means if you have x1 here and x2 here, f of x1 is less than f of x1 is less than f of x2. So here in this case, if f x1 is here and x2 is here, now always f of x1 is greater than f of x2. So that's called decreasing function. And also you know that the f prime of x less than 0, here for increasing function f prime of x greater than 0. So both of these can be proved by using mean value theorem, right? Can be proved by using mean value theorem. Uh, that's a one of the other benefits or consequence of having a mean value theorem in here. And one other thing that I want to cover here is that the how to find whether the critical point is a minimum or maximum, whether the critical point is minimum or maximum. So let's say you have a minimum. So at a minimum, it's uh, you can draw um, we can draw function like that. So it's f of x and x. You can see that the tangents drawn to this line at different location. That means the slope of the tangent line or the derivative at that respective locations. We can draw like that, derivatives. Now here f prime of x, slope, right? Here is 0. Now it's negative, right? So if I draw here the curve of f prime of x with x. Now what happened to f prime of x here is that let me erase this line, and I want actually somewhere here x. F prime of x is negative. First to start with a negative value, right? And it becomes 0, right? And it becomes 0. and then it starts increasing to positive, right? So the sign of f prime of x changes from negative to f prime of sign to positive at this kind of a place. That means a minimum. Now, if you have another case, if you have another case, f of x, so we have maximum, and then I'm going to look at how f prime of x also changes. So at the beginning, f prime of x, that's the slope of the tangent line drawn at different locations, is negative, 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 right? So it's positive value, and then zero, and then becomes negative. It becomes negative. The slope of the tangent line. Slope of the tangent line becomes negative. So the first, at first, it is positive and becomes negative and becomes zero and then becomes negative. That means f prime of x sign changes from positive to negative. So that's a maximum, and this is a minimum. See the case? When the sign of f prime of x changes from negative to positive, it's a minimum. When sign changes from positive to negative, it's a local maximum. Positive to negative is a local maximum. Negative to positive is a local minimum. So there's another case where we wouldn't see sign change. That's called uh, in point of inflection. Point of inflection. At a point of inflection, what would happen is we have a curve. Something looks like this. So it's kind of here point of inflection. Point of inflection. It's not a local minimum or maximum, but this would become a critical point because f prime of x could be zero, but the sign of f prime of x. So if you look at the sign of f prime of x, if you look at the sign of f prime of x, so if you look at f prime of x, so this is at this point it is positive, positive, and becomes zero, right? And then again increases positively. So I can draw something like that here. So it's at the beginning it is positive and becomes zero and then goes up, right? The sign doesn't change. The sign of f prime of x does not change. It's a point of inflection. So if we know that f prime of c is zero, it is a critical point. F prime of c is zero, critical point, or if prime of c does not exit, it is a critical point. And then we can also find the sign change to see whether that critical point is a local minimum or maximum. So that's also another consequence of uh, mean value theorem and increasing functions and decreasing functions. Uh, so that means in this domain the function is decreasing because f prime of x is negative, right? And f is positive, it is increasing. So decreasing and then increasing, it means a minimum, and then increasing and decreasing is maximum, right? Increasing and decreasing is a maximum. So we can find uh, whether any critical point is a uh, local minimum or maximum or an inflection point. One other special case, one other special case of mean value theorem, special case of mean value theorem. Special case of mean value theorem is called Rolle's theorem. In that case, in the Rolle's theorem, it says that uh, if f is continuous and on AB and differentiable on AB, so let's say you have something like that, it's continuous if f continuous on AB and differentiable on AB, then there exists number C between A and B, between A and B, such that f prime C equals 0, right? AB, if f is continuous on AB and differentiable on AB, and this is one part, AB, and if A equals FB, then there exists number C such that f prime C equals 0. Now, the mean values theorem says that f prime C equals FA, sorry, FB minus FA over B minus A. So f if f of A equals f of B, then f prime C equals 0. So this is this Rolle's theorem is a special case of mean value theorem. So special case of mean value theorem. What this say is that we have uh, some function, right, where actually you have close interval A and B, both FA and FB equal. That means there's a C. That means according to mean value theorem, you can draw parallel lines to this FA and FB secant line, and at some point it would become the tangent to the curve. And that point, this one has f prime of c equals 0. That's Rolle's theorem. Uh, that's a special case of mean value theorem. So let's use this mean value theorem and its consequences to find the maximums and minimums and analyzing critical points on functions. So I will include that in a different video. And if you have any questions for this video, please post them, and I'll try to answer them. Thank you very much.